This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hey, can you hear me? Can you hear me? In the back? No? Yes? I'm not. Oh, you can hear? Okay, cool. Just turn it up a little bit. Yep. Great, thanks a lot. So, we're in the middle, today we're in the middle of the kernel methods topic. We're on the second of 3 decks, and there is another one later on that kind of comes back to kernel methods. So last time we began on this deck after deriving the hard margin SVM with geometry. Okay, so we motivated it by wanting to maximize margin. That was the heuristic. And then we worked out how to measure margin with some linear algebra, with some projections and some lengths of things. And then we massaged that until we had a nice form for the hard margin SVM to make it into an optimization for training. And we also had a view of that as a loss function. Okay. So we started on this deck, and in this deck we're relaxing the hard margin SVM. So one view which I started on last time was relaxing the loss function, so that it doesn't just give infinite loss when you make a mistake, but it sort of gives more and more loss as you go. And then what we're going to get to is turning that into a more convenient to work with optimization that isn't sort of written in that way by introducing slack variables. And so along the way, I'm also going to then transform that optimization into an equivalent one via Lagrangian duality. And so if you take a subject in advanced optimization, you might learn about duality. And one thing that's nice about this topic actually is you see like a really nice worked example. So it's not so abstract because there's a particular thing we're trying to do. And what you get out of doing that, like what's the point? The point is that you have 2 ways of solving the SVM that all practical software libraries use, and they have different computational complexities, different runtimes. Okay, and then that's going to set us up also for introducing the kernel, which is how we make it nonlinear. Okay, so this was the hard margin SVM. We just are looking for a linear classifier that maximizes margin, and what we got up to was this optimization formulation. And so one thing I've done since Thursday is I just went over this deck and reposted it to LMS with the B's added in here. But it's easy to forget them because the objective function isn't in terms of the B's at all. It's actually just in terms of the W. So it's the W that it's affecting the margin, but the B's come into these constraints, which are saying we need to not only get everything right, but we need to kind of be pushed away from the decision boundary as well. So that's what we have here. Now, so sometimes in this deck you'll see a half out front. Sometimes we'll have a square here. It makes no difference because multiplying by a half, taking a square, is an increasing transformation, and so that's the same problem. Okay. So that's what we got up to. This is the margin. This is like regularizing. This is like training error. Perfect training error, and we want to regularize. Okay, and we had this picture, right? So those are the things we did. Okay, yeah. Okay, so that was the expression for the margin, and then we set it to be a particular value, like deciding what 1 centimeter is. You know, we can have different measures of length, but we need to define 1 centimeter. We need to resolve the ambiguity. Otherwise, there were lots of W's that would give us the same solution. We wanted to not have that because it's nice to have unique solutions for our optimizations. So that's why we did this step. We had the freedom to do that. So we've done this already. We want to be nonlinear, and we want to allow mistakes. It's okay to make mistakes. So last time we had talked about an equivalent way of looking at the constraints was thinking of a loss function. So if we were learning to minimize the length of W plus summing up this loss function, it's the same thing as the hard margin SVM. And so the natural thing to do is not penalize infinitely much mistakes, but instead penalize how much we make the mistake by. And that leads us to the hinge loss. And this is what the hinge loss looks like. So this is what we were pretty much up to. So what we want to do next is transform the hard margin formulation to be able to make use of this loss function. Okay. So this is the soft margin objective. We just changed the loss function. And here's the hinge loss written in one line. Now, it's not clear how to transform this into a dual formulation. It's not clear how to add the kernel to this. And also this loss function has this kink. So this is a kink here. So even though this function is continuous, I can draw it without taking the pen off the page. I can do it in one stroke of ink. The derivative doesn't look like that. The derivative jumps. Okay, it goes from like -1 to suddenly being 0. Right? And so that's not so nice either. So what we do next is rewrite the hard margin formulation without this loss function thing by sort of making use of this by introducing some extra variables. Okay, so we're going to make it more amenable to analysis. That's what we're doing. So in optimization, the idea of slack variables isn't a machine learning idea, it's an optimization idea. When you're playing with optimization programs and you want to transform them, one of those days, we add slack variables. And so slack variables, you can think of them as taking up slack, allowing you to relax a constraint. So you permit violation of a constraint by sort of adding this thing in there that is allowed to take on some amount of violation. And then what you typically do with slack variables is you penalize for them. So if any of your slack variables have some value in them, they're not just 0. So 0 tends to mean there's no violation of the corresponding constraint. Non-zero means there is some violation. Then when they're non-zero, we want to penalize that. Because we don't like violations of constraints. We just, allow it. So that's kind of what we should expect when we're doing this. We should expect that something like that's going to happen. So what we do is for every training example, we're going to introduce a corresponding slack variable, which is we want it to be an upper bound on the hinge loss. Okay, so we're going to permit hinge loss. It doesn't have to be 0. It can be something positive, that's fine. And we kind of want to store the value in these Greek symbols, which are pronounced xi. So it's spelled xi and pronounced xi. And we can do this equivalently by introducing 2 constraints. So we're kind of introducing this new variable that like W and B, the optimization needs to choose. And we also need to introduce some constraints involving it. And we also need to introduce it to the objective function. So the first step is we want this to happen. So we can do that by adding 2 constraints that look simpler. Because you don't really like functions like this in optimizations, because functions like this are kinky. They don't have derivatives. But these ones are nice. This is like a linear function, and this is a linear function. So we're kind of taking one nasty thing and turning it into two nice things. And the reason why this is the same as this is because we're going to add to the objective, right, that we want the size to be as small as possible. But also you can see if psi is bigger than this term and it's bigger than this term, it's got to be bigger than the max of the two, right? If C is bigger than A and it's bigger than B, then C is bigger than max of A and B, right? Same thing. Can go from one implies the other two implies the one. So it's an exactly equivalent set of constraints. Okay, so that's the first step. We're going to have these constraints. And then the other thing we're going to do is add to the objective that we're going to penalize based on these psi's. So that's like having the loss function in the objective, which is, after all, what we're trying to do. If you look at kind of reformulating, that's what we're setting out to do. We're just trying to relax the hard margin problem when we had a loss to this soft margin loss, this hinge loss. And so we're still going to be doing that. We're still going to penalize by these slack variables. Now, if you're watching carefully, you might worry, yeah, but Ben, you didn't set the size to be equal to the LHs, to the losses. You just set it to be greater than. So what's stopping us from penalizing more than necessary? Because what if the psi took on some really large value, bigger than the corresponding loss? Well, it's because we're minimizing. We can choose the size freely. And so what happens is the size, because we're minimizing and we've got this positive function of the size get pushed down by the optimization as much as possible because of the minimization, and they get pushed down to actually be equal to the LHs. So even though I've written it as greater or equal to, they're actually going to end up being equal to because of the minimization. So that's kind of cool. So I kind of introduced it this way, but because I coupled that with putting it in the objective, it's really equal to. So you can think of the size as absorbing violation. You can also think of them as just representing this max function. It's like a way of having the max function without having the max function. That's kind of what I'm doing. And another thing that I've introduced is this C hyperparameter. So this C hyperparameter, it's like what we had with ridge regression. It's something you have to tune. There's not really any basis for like choosing what its value is. We don't learn it. It's just something you have to try a bunch of values out. You have to do grid search. Sometimes in SVM software it is called C. Sometimes it's called like the regularization hyperparameter. Sometimes it's called like the soft margin parameter. Sometimes it's got a different letter like lambda or something. But it's something that we choose. And sometimes it appears in front of this term instead of this term. But that doesn't matter. Because I could just multiply this whole thing by a constant like 1 over C. Right? It'll kill this one and I'll get a parameter here. Makes no difference where it appears. And it's controlling the trade-off between regularization and training error. That's the way to think about it. We're deciding how much we're happy to overfit or underfit. So this is a thing that we have to tune. And then otherwise we just have what we said, right? So this is the SVM. Like we're pretty much there, but now there's a bunch of extra things we can do. So just to recap, we're maximizing the margin. We're choosing a linear classifier that maximizes the margin, that's this term, or minimize the length of W. And we're minimizing training errors, and we're allowing there to be mistakes by having these slack variables. And this is equivalent to trading off hinge loss with regularization. Okay, cool. So that's the soft margin, and like side by side we've got this. Okay, so you can see we've relaxed or softened or whatever by allowing these violations. And as I warned, we've got this half now in the objective and this square, but it doesn't change it at all. It's equivalent. So I've written this to make it look like this. And of course the reason I do this is if you're taking a derivative of the objective with respect to W, it's nice to have the 2, the square. If you didn't have it, you would get square roots. So you don't want that. So the square is actually handy to have. It makes the derivative nicer to work with. And then the half just gets rid of the 2. So like, you know, the derivative of this is just w basically. So that's nice. Because we kind of need to do derivatives to do more with this. But there'll be green slides. But anyway. Okay, so that's the soft margin SVM. But we're still just linear, and all we've gotten is we're allowing mistakes. But we haven't really bought anything else. So now what I want to do is give you a bit of a taste for some more optimization stuff, but in a useful way, right? So I'm going to talk a bit in generic terms for like one slide about what is Lagrangian duality. And then I'm going to have some green slides where I go and apply that idea to the SVM, where I go through how it works. And then I'll show you the result again in white slides, okay? And what we're getting is another way of training the SVM, and it's going to allow us to choose what kind of runtime we're going to suffer, and it's also going to make it easier to kernelize in the next slide deck. So there's very much a reason, there's something you get for this. It's not just pain with no gain, okay? But the cool thing is you learn some extra optimization for free, so that's good. Okay, so these are really powerful, useful ideas when you're doing optimization. So it's handy to sort of create a language for talking about optimization. And since we're talking about generic tools for optimization, it's handy to have a generic way to talk about a constrained optimization program. So in optimization, it's conventional to talk about minimizing things. There's no difference between minimization and maximization. There's a minus sign. Doesn't matter, right? But just so that we don't get muddled, I'll be talking about minimizations, and conveniently the SVM is written as a minimization. So we're going to minimize some objective function f, and there are two kinds of general constraints you can have. You can have inequality constraints, like these g's, and we don't have to be less than or equal to 0. It could be less than or equal to some other function with respect to x. But we can move all of that junk over to the left-hand side and make it a 0. And we don't lose any power by doing that. We just have a nice standard language. This is standardizing. This is like having the metric system. This is like metric system for optimization. So we can have inequality constraints like this, and we can have equality constraints like that. And equality constraints can also be written as two inequality constraints. You can have hj of x less or equal to 0, and then you could have another one, hj minus hj of x less than or equal to 0. And that together, that would be the same thing as hj of x equal to 0. So in a sense, you don't necessarily have to have these, but they're so common, it's useful to treat them specially. Okay, and again, we're thinking about like submerging ourselves in a lake, but now we've got we've got some constraint. We can only sort of be within some feasible region. That's the way to think about constrained optimization. And we've already been using constraints in the SVM. Okay, so you can do gradient descent for these kinds of problems. There's something called projected gradient descent. You can do constraint stuff. But what we want to do is transform the problem to another problem and understand maybe another way of doing things and maybe even another way of applying gradient descent. So the hard margin SVM looks like this. If I rearrange the constraint, I can have it less than or equal to 0. So one way to view what we're going to do is what Lagrange, like the method of Lagrange multipliers or Lagrange duality lets you do, is it lets you move constraints into the objective function. It lets you turn constrained optimization, where you're, say, minimizing just with respect to, say, x. Don't confuse x here with data. It's just some variable you're minimizing with respect to. We can turn that into a two-level optimization where we have no constraints at all. So we're trying to sort of get rid of constraints because we don't know how to deal with them, or so that we can kind of just think about optimizations without them, so that we can swap orders of things, that kind of thing. So one idea is we can transform to unconstrained optimization. And then another thing we can do is we can then transform our original problem, which we're going to just call primal because it's first, not because it's special, to another problem, and let's call that number 2, so dual, right? And we can actually alternate between them depending on what's interesting. And we can look at what conditions we need for like analytical solutions to these things. So remember when we did linear regression, we were using what I called first order necessary conditions, which was that the derivative was 0 at the solution. We can extend that idea to constrained problems by thinking this way. So when you've got constraints and you're using the method of Lagrange multipliers, you still can have necessary conditions for solutions, but we have a few extra ones. Okay, so let's go and see what happens. So the first thing we can do is introduce what's called the Lagrangian function. And what's a bit annoying about this area is the word Lagrange just appears a million times, and it's really easy to like muddle up these ideas because the names sound so similar. So there's this special function called the Lagrangian function, and it's basically just your objective function plus soft penalties for your constraints. So we now no longer have hard constraints, we have soft constraints. So it might be okay to violate them, but we want to penalize. And we might penalize by so much that you don't violate them. And we want to have some kind of like currency exchange rate for penalizing constraints versus doing well on the objective. Let's call that currency exchange rate like lambda and nu. It looks like a V, but it's a Greek symbol nu. So if we crank up lambda and nu, right? If we really crank it up a lot, like imagine taking it to infinity, then we're not going to violate our constraints, right? It doesn't matter how good our objective looks if we deviate from our path, from our constraints. We're not going to do it if the penalties are big enough. So the idea is we're introducing more variables, which is like, that sounds painful. We're getting rid of the constraints, which is good. We're just turning everything into unconstrained optimization. But we're allowing these new variables, they're called Lagrange variables or Lagrange multipliers or dual variables, because they're going to become the only variables of the other formulation. When we're finished, the x is going to disappear and there'll be no more primal variables. In the language of the SVM, that's W and B. W and B will actually disappear when we go to the dual. We'll be left with new variables. So, but the idea is if I was allowed to like set x, nu, and x, lambda, and nu at all in any way I like, I could set lambda really big and nu really big, and it would be equivalent to solving my original problem. That's the idea. That's the idea of Lagrange multipliers. And if that sounds kind of intuitive, if you read a little bit of an optimization text, and in the first lecture I mentioned a book by Boyd and Vandenberg, which is this blue book, Convex Optimization. It's free online and it has all of this stuff in detail. But if this feels a bit intuitive, if you look at that, you'll probably get it pretty quickly. Like you're probably like 95% there. So, but it's not this isn't an optimization subject, so I don't want to go that far. So what I've argued for is the old program is equivalent to this line. I've hand-wavily proven that minimizing this after cranking up lambda and nu as much as I need to is the same as minimizing the original constrained problem. And so that in maths, it's this bi-level optimization. So there's a max inside a min. Okay, so I've kind of gotten rid of constraints, but I've kind of gotten another level of optimization. It's not necessarily better, right? So to just say again, I'm allowed to like crank up these exchange rates as much as I want so that you pay attention to all of the constraints, and then I just minimize as before, right? And so that's actually the same as the original program. And you can prove that very rigorously. And then the only big idea left is that when I swap the order of these optimizations, which seems very random and arbitrary, I get a brand new optimization problem. And the values that these optimizations might take, the solutions might not be the same. There's nothing saying they're the same. or necessarily a good idea. It's not obvious it's a good idea. However, there's a famous theorem, the key result in duality, which is called weak duality, which says that solution to this, so the value that the Lagrangian function takes, whatever value this objective plus penalties takes at the solution of the dual, lower bounds the solution of the primal. So if I'm looking for if I don't want to solve the primal for some reason, okay, like it's too expensive, but I'm willing to solve the dual, no matter what program I'm doing, this is amazing, no matter what program I'm doing, solving the dual will tell me something about solving the primal, even if the dual is a lot cheaper to solve. And so this is an idea that happens in algorithms and stuff as well. A lot of approximation algorithms use these kinds of ideas, sort of converting to something easier and then getting like a bound on the answer. So this happens no matter what, like really very little or no conditions on the programs. Like it's very powerful. Just swapping the order is enough to guarantee that. And I haven't said why this should be. It's a leap of faith, right? But if you think about it a lot and you read about it, you can sort of read a proof of the weak duality theorem. Now, there's another really cool, important result, and it's one of the reasons why computer scientists, statisticians, mathematicians, and engineers love convexity. If your program is convex, which so much of machine learning and statistics is, but not all, then there's actually no gap between primal and dual. They actually are the same. So the solution of one is the solution of the other. So that's guaranteed if you have convex programs. So you can really solve one or the other, it doesn't matter. You can go between them, they have the same solutions. So that's super powerful. Yeah, question? Both. So both F has to be convex, and the constraint sets have to be convex sets, which corresponds to maybe the functions, maybe not the functions being convex. You've got to be slightly careful what you mean. But if you think of G as tracing out level sets, you kind of want to fill them in and that thing be convex. But basically, if you think of this picture, you want the constraint set to be a convex set. So you draw a line between any 2 points in the set. It can't leave the set. So these things have to define convex sets. And then the function, the objective function has to be convex as well. And the SVM satisfies that. Yeah. Cool. So this is called strong duality. Okay. So this is telling us we have a green light to play with duality to maybe get a different way to solve the SVM. At the end of the deck, or I think actually more accurately in the next deck, there's a shortcut. You don't have to try out duality to see what's going to happen. There's actually a shortcut called the representer theorem, which tells you what's going to happen before you do it. And I'll get to that, and it will make sense when I get to it. So now we're entering some green slides, which, to remind you, means I'm kind of going a bit deeper than I expect, students leaving the class to feel comfortable with. I think it's important for you to see it, which is why I'm not just saying go look at it in your own time. I want to go through this, but to put it into crude terms, this isn't examinable. Okay, but it's good for you to look at it. Okay, so what about solving this Lagrangian function? Can we talk about like what conditions on this thing must hold at an optimal solution? So we don't just have a program with respect to X anymore. We've got all of these other things. And we might want to have some constraints on lambda and nu. Like, for example, if we're minimizing this L, this calligraphic L, this kind of curvy L, we might not want the lambdas, for example, to be negative. Okay? Might not make sense. So we need to kind of figure out what are the conditions that all have to hold at a solution. And so those conditions have a name after the people that independently discovered it, and I think there's a fourth person as well. So these are called the KKT conditions. If you ever see KKT, it's referring to basically extending the idea that the derivative has to be zero at a solution to some more conditions. So what are they? Okay, so we're like kind of souping up the idea that the derivative has to be zero at a solution. So the first set of conditions are that the original constraints, all of the original constraints have to hold at a solution. It doesn't make sense to have any of the constraints not holding, because how could that have been a solution to the original problem? Doesn't make sense. So we need all of the g's to be less than or equal to zero at the solution. We need the h's to be zero. Okay, so that's easy enough. We also need that the dual variables for the inequalities, they need to be non-negative. That's because if they're allowed to be negative and we're minimizing L, we could kind of like we could make L smaller and smaller and smaller forever if we made any of these lambdas negative. Because for feasible x's, right? For feasible x's, remember, g is negative. So we don't, sorry, I'm saying this the wrong way. When g is feasible, right? When g is feasible, we've got a negative value here. And so we don't want to penalise when that's the case. That's what I'm trying to say. So we don't want to penalise when it's the case. Negative is okay if g is negative. But if lambda were allowed to be negative, this thing could be large and we might be penalising. So we don't want that to happen, right? In fact, when g is negative, what's going to happen is we're going to want to set the lambdas to be zero. We don't want to penalise when g is happy. And when h is happy, these terms are automatically going to be zero no matter what we set nu to. So we don't have to worry about constraining the nus at all. Okay. And so this idea about we either need g to be feasible or we need lambda to be sort of non-zero, that is represented by the condition called complementary slackness. Okay? So the way to think about it is if g is negative, we don't need to penalise, so we need to set lambda to zero. So that means the product will be zero. If g isn't satisfied, right? If g isn't satisfied, this thing will be positive. And so we're going to, am I saying this in the right way? If g is not satisfied, we're going to set lambda to zero. And if, no, I'm getting this muddled. Don't penalise if constraint is satisfied. Yes. Yeah. Okay. So if the constraint is satisfied, g will be negative or zero, in which case we're happy either way, so we want to set lambda to be zero. Right? If g happens to be zero, we don't need to set lambda to zero. It's fine if it's greater than zero. So that's the idea. Okay. So these things together are ensuring, right, that this thing, because actually there's this kind of little, there is a constraint here. When I said there are no constraints at all, I lied a little bit. There are no constraints on x anymore is what I meant. The KKT conditions are guaranteeing that at a solution this corresponds to this, the solution of this. That's what they're guaranteeing. And if you look at the Boyd and Vandenberg book, for example, or any book on nonlinear optimization, there'll be like a whole chapter on this. Okay. And then finally, we have our usual suspect, that the derivative with respect to the primal variables is zero at a solution. Okay. So it's like we kind of expect that one to be there, and then we've got these constraints, and then we've got this slightly tricky one that's just saying that we don't penalise when the constraint's satisfied, because otherwise we basically are going to be messing up optimising F. Okay, so what can we do with this? Well, we can apply this to the hard margin SVM. So in this part of the deck, I'm only applying these ideas to the hard margin SVM, but all of the same ideas hold for the soft margin SVM. It's just a bit more involved. Okay, so now what does the Lagrangian look like? I've got my objective function, and if I write my constraints as g of x less than 0, and then multiply them by lambda and add them up, I get this. And it's an inequality constraint, so I have to have lambdas, not nus. And there are no equality constraints. So this is my Lagrangian function. And if I go through all of the KKT conditions, I get these conditions. So this is what I'm working with. Okay, so this is what must hold at a solution. And so what I can do now is use those conditions to eliminate W and B altogether. So that's what I'm going to do. I'm going to get a system of equations by basically solving the derivative equals to 0. But I've got enough information not to solve it, but I've got enough information to at least eliminate the W's. So I'm not somehow doing some magical thing where I'm solving it and getting a closed form solution. That's not what's happening. I'm really just trying to eliminate W and replace it with lambdas, because lambdas are my new variables. So the first set of equations comes from the derivative with respect to B. Okay, so this is the stationary condition. And then I get a whole lot of equations like this, one per training example. Okay, and I have a lambda per training example. And so you can kind of look at this and see immediately I could solve for the W's, right? And anywhere I've got a W here, I could substitute it for this expression. So this one gives me a new constraint, and then this one is going to let me eliminate the primal variables. When I substitute that back into the Lagrangian, I get this function. Right? Because I'm getting like a sum of W's, and each W is a sum, so I get a nested sum. And I get this thing. Okay, and notice there's no W and there's no B. I've eliminated the primal variables. Also notice I've only got dot products between the x's, the training examples. The only place that the data, the training data, enters into my optimization now is via dot products. And that's going to be important in the next deck. And so I now have a new objective function, and I have some constraints. So one constraint is this one, and then I have some other constraints that come from dual feasibility. So I can't ignore these. And so when I wrap them all together, I get, ta-da, the dual program. And this is a max. Because going back a few slides to one of the last white slides before the series of green ones, the dual program involves maximizing, not minimizing. Okay? So what strong duality tells us is that because I had a convex program, I can compute what the dual program is by applying the KKT conditions, can massage it and replace the primal variables, and I end up with something, and it's going to be equivalent. In some way, it's going to be equivalent to solving the primal. Okay, and so this is the new thing. And you might be wondering, how is this any better? It looks kind of ugly. I don't understand the intuition of this anymore. Well, let's talk about that. Okay, so it's still a quadratic program. So it's still sort of the same kind of runtime, except the runtime is different now. It's not in the dimension of the problem, it's in the number of training examples. Because that's how many lambdas we have. Whoops. And so that's what I've said. It's cubic in the number of training examples, not the number of features. And also critically for the next PowerPoint deck, the program only involves dot products. So that's going to let us kernelize. And we'll get to that soon. So before we get there, let's just like close the loop on everything, because there's something weird that's happened. Like, how do I use this to predict as an SVM? Where's the SVM gone? Where's W gone, right? I've got these lambdas and no W's. Well, if you solve the dual, you can use it to make predictions. Okay, so firstly, we can recover the W's if you want. Right, so we had from the stationarity condition these equations that allowed us to get back the W, the components of the W. Okay, so this is This is what we had. So you can always get back W this way. And the way we can get back B is by using the complementary slackness condition, which said, it's this thing. No, not this thing. This thing here. So this was complementary slackness. This was saying pick any training example, right? Pick any training example you like, and you can take its dual variable multiplied by the corresponding g, and the product of those things should be 0. So what that means is if we take any training example, right? We can potentially, for any support vector, which we're going to define in a minute, we can recover the B. So let's see how we can do that. Okay, so I'm trying to show you how you can recover the W and B if you want. So if you take any example for which the corresponding lambda is greater than 0, and those are the examples that we're going to call the support vectors, which I say in the slides in a minute. So for any I for which lambda is greater than 0, and there's got to be some, then that means from complementary slackness that other term had to be 0. If you have a product of two things and the product is 0, and one of them is not 0, then the other has to be 0. Okay, the only way to get 0 is one of the two things in a product to be 0. Right, so if we know that the lambda isn't 0, then the other thing had to have been 0. And so if we rearrange that equation, we get this. So this is coming from like the hinge loss constraint. Right, so this is like y times y hat has got to be equal to 1. Right, and so if we've solved the dual program, we've already got our lambdas, we've got our training examples, y's and x's. We can divide both sides by y and then put b on one side and put the rest on the other side, and that can give us b. So we can recover b from any one, what we're going to call support vector. Now, if we have a new test point, how do we make predictions for a new test point? That's easy. We just need to do w.x plus b. Well, we can get w from this expression, and we can get b from this expression. I'm just not writing it down, but we can get it from this expression. And so if I just have a new test point x, I just need to dot it with this thing. So that's what we've got here. And I need to add on this b offset. And this is really cool, because it means to make a new prediction, I'm like looking at the similarity of the new test point with all of the training examples, weighted by their dual variables and their training labels. And we're kind of like, so it's like a similarity, it's like a weighted similarity, because dot products is a form of similarity, right? So a new test point comes along, and I want to know, how do I predict you? Well, I compare you to every training example by dot product similarity, and then the more similar the training examples are, I have like a higher vote for their training labels. For the less similar you are, like if you're orthogonal, you get no vote at all. And so also, somehow the more important the training examples are, the bigger the lambda, the more weight we're going to have as well. So there's some intuition as to how we make predictions with this thing. So the point is, if I solve the dual, I can still make predictions like I'm an SVM. So I don't actually, and notice I could do this without ever actually writing the W down. I didn't actually need to write the W down. I just substituted it in here. So the powerful idea is I don't actually have to like recompute the primal variables except for B. Okay, so training just involves finding a lambda that solves this. And what I've done in this slide is, before I was talking about the hard margin SVM. Now I'm talking about the soft margin SVM, because I hadn't derived that for you. All of the same steps happen, and the only thing that changes is I now have an extra constraint on the lambdas. If you imagine that each lambda, and we've got n of them, is in between c and 0, what does the vector look like? It's inside a box. It's inside a box of side length c. That's what that looks like geometrically. So these are sometimes called the box constraints. And so this is super cool because now we have another interpretation of what C is doing. Remember, the bigger that C was, the more we were penalizing training data. If we were allowing C to be really big, we were letting the training data have more influence. If we made C really small, we were saying, I don't care about training data, I want big margin. So if you think of making predictions like this, and I'm saying lambdas can be really big, that's like saying individual training examples can have lots of influence on this weighted vote. But if I'm constraining the lambdas to all be really small by making big C small, no single training example can have a very big influence. And so like I'm maximizing margin more. So that's some intuition there as well. And we make predictions exactly the same way as in the previous slide. So putting it all together, we just have a linear classifier. Okay, this is like your guide. There's a linear classifier, no different to perceptron in terms of model, no different to logistic regression in terms of model really. But we want to choose a linear classifier that maximizes margin. That's our heuristic, because we think that's going to generalize well. And there is a lot of theory that I haven't talked about that says it's a good idea. We figured out how to write margin as a mathematical expression with a bit of linear algebra. And then we could write that down as a constrained optimization. Okay? A nice quadratic program. This is how you train a hard margin. But we didn't want to be hard, we want to be soft. So we introduced slack variables, and then we can come up with an equivalent way to train it by looking at the KKT conditions and using them to eliminate W and B. And that led us to a dual program. So this is the hard margin version of it, but the soft is just the same with an extra constraint on lambda. And so there it is there. And so we can train and we can make predictions. Okay, so we can do everything that we want to do. So a little, just sort of closing the loop on what is a support vector. So we had this complementary slackness condition that I got momentarily confused about, which says that the lambdas either have to be 0 or we have to be exactly on the margin. But what does exactly on the margin mean? You know, when you first learn about an SVM, maybe before this subject, or just like in your own time, you sort of learn the support vectors are the things that are on the margin or they're on the wrong side. So that's exactly what the complementary slackness is saying. Okay. So we might have a lot of points that are outside the margin. So we're satisfying the constraint. We're on the right side of the boundary and we're far from the margin, no problem, lambda 0, complementary slackness is happy. But for a few points that are on the margin or on the wrong side, the constraint is not satisfied. Right? And so we have lambda non-zero. And those are the only ones that have a vote. Only the support vectors are determining W. Any example that is outside, that is very happy and far away, on the right side, doesn't even influence W. It has no influence. That's amazing. And you wouldn't have known that if we didn't go to the dual formulation. You wouldn't have really known that by looking at the primal. Okay, it's not obvious. I mean, you could think about the loss and kind of convince yourself there. It is possible. And so we're really only needing to keep around the support vectors if we want to make future predictions. You can throw away all of the other training examples. So in terms of storage, you don't need them. So that's the name support vector, right? They're sort of special ones where the dual variables are non-zero. So I've already sort of hinted at training. It's a quadratic program. There's off-the-shelf software. It's either this complexity or that complexity. Using off-the-shelf can be inefficient. There are special purpose packages that are even for this particular kind of quadratic program. And I talk a little bit about it here, but I'm not talking about it in much detail. So it's more of a pointer if you want to read more about it. I'm kind of introducing some of the ideas and mentioning some of the keywords you could Google on. But I'm not telling you how any of that works because it's a whole, series of many lectures to explain exactly how you optimize the SVM super efficiently. But you wouldn't do it yourself, right? But you could do something less efficient yourself. That would be possible. So that's the lecture, and we're right on time to finish. So I've done the soft margin, we've relaxed violations, that's fine, and we've done this really kind of abstract, weird dual thing. And next time we're going to get even more value out of the dual by kernelizing. And that's when we get to be nonlinear. Thanks a lot. See you Thursday.